So our next speaker, I guess David, are you online right now?
I am. I am
All
here.
right, awesome, awesome. Good to hear that. So as I said, now we are going to talk about machine learning again. And David is going to talk about machine learning from a very different perspective. David is the founder and executive director of ML Commons, where he helps lead the ML Perf benchmark and other initiatives. He has over 16 years of experience in semiconductors, computing, and machine learning. He founded a microprocessor and compiler startup, was an early employee at Asta Data System, and has consulted for industry leaders such as Intel, NVIDIA, KLA, Applied Materials, Qualcomm, Microsoft, and many others. David holds a Bachelor of Science degree with honors in mathematics with a specialization in computer science and a Bachelor of Arts with honors in economics from the University of Chicago. So now I'm going to hand it over to you, David. Really looking forward to your talk.
Absolutely. So thank you very much for inviting me here, and thank you everyone for taking your time to join us. I guess I left it off my bio, but I also have 3 patents related to camera design. You know, you can let me in as an honorary engineer, even if by training that's not my core expertise. You know, thank you for the warm introduction. So I'm going to talk about kind of the intersection of ML and automotive and ML Commons and what we do. To start with, for many of us here, we might be members of IEEE. That is a great example of a organization that focuses on collaborative engineering, right? When we come together at IEEE, we build standards. There are standards for functional safety and ISO that Junpei alluded to. There's a lot of open engineering organizations out there. ML Commons is one of those. There are also a lot of AI-oriented organizations. And when we started ML Commons, we looked, but what we saw is that all of the AI and ML organizations were really not focused on engineering. And so we are at the intersection of those two things. We want to be building tangible engineering artifacts, and we want to be an open global community. And that is what we are. We have members on 6 out of 7 continents. If there's anyone here from Antarctica, let me know. You should become a member. Then I get 7 out of 7. You know, we have leaders from all corners of the ML and silicon space. You'll notice many leading chip designers up here and from all over the globe, right? We are truly open to everyone. Huawei, Inspur, both on the entity list, they are members, and we value them just as much as every one of our other members. We also draw heavily from academia. The founding of our organization was really with 6 organizations, and 3 of them were academics and 3 of them were commercial. And so we have, you know, over 50 members. And all focused on our core mission, which is making machine learning better. So I already gave away the mission. I look at our mission as really having 2 critical pillars that I'm going to talk about here. I've highlighted in bold. One is benchmarks and one is data sets. And those are, I think, 2 of the most important ways we can make machine learning better. And I'm going to talk in detail about what we're doing and how it relates to specifically automotive. And there's a very big role that we play in the silicon side. So why benchmarks? So I want to start out with some high-level executive math. If you're ever at like TED or some conference like this, this is sort of pitched here. And so I'll go through it quickly because I know we're all engineers here. The key point is that this modern era of machine learning has been unlocked by big data. So this is a chart taken from Andrew Ng's group at Baidu Research from about 7 years ago. The axes here are on a log scale. And so I think the key thing that this slide really captures is that when you don't have a lot of data, machine learning doesn't work. And that's what happened in the 70s and 80s. And even in the 90s, it just didn't really work. But once you get enough data, you have this power law region where your performance, your accuracy really improves at a very rapid clip. And the key point I want to mention here is that somewhere on that curve, in that power law region, are key features that bring us all joy. Sometimes it's the ability to do red eye reduction. Sometimes it's full autonomous vehicles. Sometimes it's lane keeping. Sometimes it's machine translation. But all of those things should be on that curve somewhere. And this was found for a variety of different types of neural networks, all different sorts. And so this is why machine learning is so big, is because we're able to get more data and drive up our capabilities over time. But if we have big data, we need big models. So this is again, logarithmic y-axis, or rather exponential y-axis, I should say. And this is showing the trend in the size of models that we need. So once you have big data, you need a big model to learn. And what you can see up here is that these models are improving at an astonishing rate. Right from the transformer side, those are things like GPT-3, BERT, et cetera. Those are growing in terms of parameter count by, hundreds of times per year, which is truly scary. So that's a great challenge for engineers to dig into. Now you have a big model and you have big data. That means you need big compute. So if you look at the growth in the computational needs from machine learning, it is even faster than the model size. Again, this is data from Berkeley showing the trend over time. And I think the scary number to really look at and highlight here, I don't have a pen, is that 750x per every 2 years for transformers. That's really driven by a lot of natural language processing, things like ChatGPT or Midjourney, et cetera. But even on the speech and computer vision side, that's still growing at 15x per year. So we have a lot of performance needs here. So since we're all engineers, I'm hoping we all took calculus. I remember the fundamental theorem of calculus, which is a truly beautiful theorem that relates two operations, differentiation and integration together in one theorem. So I cheekily have coined what I call the fundamental theorem of machine learning, which is really much more suitable for, say, an 8-year-old than a college student. But it goes like this: big data plus big models plus big compute equals innovation. So that's the napkin math. That's why we do what we do in machine learning. And this is why next generation semiconductors, circuit design, and architecture are all so important. So that was talking about training. As many of you know, inference is really how we put things into production. And inference is not computationally demanding in and of itself, but it is often at scale. So Facebook has given us some rough data on this. They have about 3.5 billion users. It's a lot. So they're very large scale. That translates into 200 trillion inferences per day. And if you do out the math, that's over 2 billion inferences per second, at least unless my calculator is broken. And here's the critical thing is we need to do this at low latency. Now, when you're in an automotive context, a general acceptable reaction time is about 200 milliseconds. And what that means is your inference really needs to be done in about 50 milliseconds. So you get a 20th of a second to do all of your inference in an automotive context. So where does the performance demands come from on inference? It's exactly that. It's you're consistently doing inference and you don't have a lot of time to do it. And we want big, powerful models. So how are we going to make things better with inference? Sorry, with benchmarks. So for all of those of you who work in big companies, we all have OKRs or goals. And the reason is because what gets measured gets improved. And the key point here is that benchmarks are not just about beating up vendors. They are certainly about that. But it's actually about creating a shared understanding of what does it mean to be better, right? And I think the prior speaker mentioned some of the things that you get measured on, right? Cost, reliability, quality of your LiDAR. There's a clear agreement on what it means to be better. When we started MLPerf, there was no agreement on what it meant to be better. And so in some ways, one of the most important things about benchmarks is that they align the entire community, researchers, salespeople, customers, all over the globe on what it means to be better. And as this picture alludes to, when you are working together, you go much faster, right? That is driving the whole industry faster. I'm going to breeze through this slide for the sake of time. These are some of the things we want benchmarks to do. We want them to be helpful for buying, helpful for designing. We want them to be fair, open, and adopted by the community. And there's a lot of challenges we have to deal with. ML is really a full system problem. When we look at how we drive performance up, each of these 6 things is a factor, right? At the lowest level, your silicon matters, right? As Moore's law churns, as we move from FinFETs to gate all around, that gives us better performance, right? New architectures matter, right? New implementations of chips, new circuit designs, better power delivery, all of these things drive up performance. New algorithms, better algorithms. So there's like 13 or 15 different ways to do a convolution. Pick the right one and it helps. Better software, better compilers, and system scale. When people start training large models, many times we're using hundreds or thousands of accelerators. And even for inference, today, some of the large models need multiple chips to do inference. So the goals of MLPerf, which is an open, set of benchmarks for machine learning, it's the industry standard, are up here. We want reproducible results. We want it to be fair and useful with representative workloads. And representative workloads are super important because that means our results are relevant to customers in many different use cases. So I want to talk about the MLPerf benchmark suite, what we've accomplished in the 3 or 4 years we've been around. And one of the things I'm really proud of is we go from, as I say, microwatts to megawatts. At the lowest end, our IoT benchmark suite, MLPerf Tiny, runs on 10 microwatt devices. And at the high end, some of our HPC systems and benchmarks were running on Fugaku. That is the Japanese supercomputer at Riken. That is the world's, I think, at the time, it was the world's #1 supercomputer, and we were running on half of that. So, and that's 10 megawatts. And so we have a variety of different benchmark suites, MLPerf training. I'll be talking about that a little bit more in a moment. And then maybe more relevant to automotive is the inference side, right? How do you perform your inference? And at the same time that we have a variety of benchmark suites covering, nearly every style of compute, we've matured our benchmarks in a variety of different ways. One of the things I'd call out here in particular is adding power measurement. We will be adding power measurement to training in HPC, hopefully later this year. And we've had training power measurement for inference since for at least a year, if not longer. So one of the ways that benchmarks work is they serve as a barometer on progress. And this chart on the y-axis is performance, and on the x-axis is time. And this line in blue is Moore's law. So that's what we would expect if every additional transistor linearly translated into performance. It's a bit of an assumption, but it seems like a fair one because this is a fairly parallel workload. And the yellow, pink, and purple lines, those are performance in 3 of the MLPerf benchmarks. They're computer vision benchmarks that have been in the suite since the start. And what you can see is we're beating Moore's law by about 10x. So, to everyone here who works on ML, give yourself a big pat on the back, right? Through those 6 factors I mentioned, optimizations that take advantage of data, silicon, architecture, scale, algorithms, and software, that's how we're getting 30x better performance since the start of MLPerf in 2018. So that's the impact that we can have on the industry. We help to drive better performance. So now I want to talk about what we're doing in automotive as it relates to benchmarks. So as the prior speaker alluded to, automotive is a very unique market, especially compared to sort of classic data centers. So what are some of the differences? First of all, the players are different, right? You have the auto vendors themselves, Toyota and Honda, top tier suppliers, OEMs. autonomous vehicle services. So folks doing self-driving cars and trucks. All of these folks, they're pretty different than someone like Facebook or someone like JP Morgan. They have very unique requirements and their applications are totally different. Things like lane keeping, parking, adaptive cruise control, et cetera. Those are some of the key applications. And again, very different than things like recommendation or image recognition. And then the tasks, things like perception, scene understanding, route planning, again, super different than many of the more mainstream applications of ML in a commercial realm. Natural language processing doesn't help a huge amount here. And sensor data. The data for automotive is absolutely very different from other contexts, right? Obviously, we have LiDAR. The previous speaker was alluding to the value of that. Many of the questions touched on radar. We have accelerometers, vision, and that's just a few, right? You might get vibration data as well. So the myriad sensor data makes things incredibly complicated and allows the ML to be more powerful, right? And our compute platforms are extremely heterogeneous. They're oftentimes proprietary, and the car itself is a complex distributed system. And then lastly, you have sort of a handful of other factors like regulatory approval, functional safety, reliability, and the real-time factor that all make life more challenging. So as we think about ML in the automotive space, we have to take into account all of these things. Now, my organization, ML Commons, has a unique expertise in machine learning benchmarking, but we are partnering with the Autonomous Vehicle Computing Consortium and probably other similar companies to combine our expertise in machine learning with industry expertise in automotive to build truly automotive-oriented machine learning benchmarks. So these will focus on tasks that are relevant to automotive, under conditions that are relevant to automotive, using automotive-oriented data sets. Right. And so this is taking our general expertise in ML and now narrowing it to serve a super important industry. So next, I'm going to talk about data sets and why that's so important in ML. So the first thing is you've probably heard machine learning referred to as software 2.0. And what does that really mean? If you sit back and think about it for a moment, what it means is rather than explicitly programming computer systems with instructions like C or Verilog or Python, we now use data to train a neural network or an ML algorithm implicitly, and that tells the system what to do. And that has some really profound differences. That means that our data defines what you can possibly do, right? And that's a really different mindset from explicit programming. And it's critical to wrap your head around. And what that means is that the machine learning model is kind of like a lossy compiler. It doesn't get everything right. It occasionally produces bugs, and way more often than a standard compiler. Everyone's used to compilers that are always correct, and everyone assumes hardware is always correct. Now, since we work in silicon design, we know neither of those things are actually true, but it's even more the case with ML. So when we build a data set, it's actually super hard and the consequences can be really bad. So first you start with what data do you have? What data should you get, right? So if you want to train a car to drive itself and you have no data in snowy conditions, you should not have that car driving in snowy conditions. You should go get that data from somewhere like Minnesota in the winter, right? But you need to label the data. You need to worry about errors in your data labels. So all of these things can ultimately contribute to the performance of your system in terms of accuracy and actually speed. And then you need to worry about your test data. Does the test data actually represent the real world problem? You know, we're all engineers. We're used to explicitly writing tests. Now we're implicitly writing tests. And what happens when that doesn't work out well? I'm from Seattle. And so there's a very famous bridge near Seattle, the Tacoma Narrows Bridge. And that was designed and put up. And the test data did not encompass high winds. And as a result, the bridge would shake during windstorms. And about 6 months after it was installed, it simply shook itself apart, right? So if they had the data, if the model had incorporated data for high winds, this wouldn't have happened. And that can happen in ML too, right? And so if you have bad data, you get bad models, you get a bad program, you get bad outcomes. What's worse is if you have bad test data, you won't even know you have a problem until it bites you. So very important things to think about. Our organization is very focused on building data sets, in part because of this criticality. And if you look at a lot of what the industry has accomplished, it was all catalyzed by this realization that you could build a machine learning system that beats humans at image recognition. And that was all on the back of ImageNet. ImageNet cost about $300,000 to build. It was a bunch of graduate students who did fabulous work, but today it is not a good data set. It's legally encumbered, it's small, it's not representative. And we want to build data sets that are big, commercially usable, and empower researchers and everyone across the industry that are diverse and improve. And we probably, especially in automotive, want those data sets to be compatible with regulation. So my organization, ML Commons, is actually very proud to be building some fantastic data sets. We've built 2 fantastic speech data sets that we published at NeurIPS, a leading AI conference. One is for speech recognition in English, and the other is to do keyword spotting, like your Amazon Alexa or Siri, in 50 different languages. And the latter one I'm especially proud of because it was a huge step forward in diversity. Many, English and Mandarin are very well-served languages, so is Spanish. But, a lot of languages like Basque or Catalan are not very well served by commercial data sets because they aren't necessarily as commercially relevant. And this was a huge step forward for everyone. And I want to talk a little bit with a demonstration of the power of data. So most data that we have is from the developed world because, to be honest, selling products to the developed world is the best way to make money. And what that means is a lot of ML accuracy is not great because this data is biased. And I don't mean biased in a malicious way, I mean in a statistical way. And underrepresented regions, therefore, tend to suffer the most. ML doesn't work great there. And so what we did is we actually built a very diverse visual data set that took common household objects in low-income countries and low-income regions with the income of the household. And then we've publicly released this data set and trained a model on it. And what we found is that for many of these low-income households, a classic image recognition neural network would only be about 18% accurate, which is terrible. But training it on this diverse data set, we boosted the accuracy to 70%. That's huge. That's just absolutely amazing. And this data set is public and free. Anyone can go and download it. So those are some of the things we're working on. And one of the ways that I actually think this is super critical is, again, we believe that these benchmarks in automotive will help to drive automotive performance forward and help folks to evaluate AI systems in cars. And these cars are going to become much more intelligent over time. And we also believe that in order to empower the whole industry, and especially researchers, we're going to need to start building automotive-centric data sets, just like those speech and that visual data set that I pointed out, to help everyone do the research that'll get us to more capable vehicles in the future. So if any of this resonates with you, we are an open community. Everyone is welcome. Please contact me to get involved. Go to our website, mlcommons.org. Membership is free for academics. We have public mailing lists. We have a community event on April 20th in Palo Alto, hosted by VMware. It's again open to the public. And especially if you're interested in the automotive benchmarking side, please don't hesitate to reach out to me. That group is public and open to everyone. So with that, I'd like to stop and turn it over to questions, and hopefully I haven't run over on time.
Thank you very much, David. You're still on time.
All right.
Now I'm going to select a few questions. Well, some of the questions are pretty long. Very intense.
I see there's one on network security.
Yeah, there's one more network security. So maybe let's start with the simpler one. So, so there's one question from one of the audience, right? he said the current ML perf for NLP only have BERT model benchmarking. Is it going to have GPT model in the future?
Yeah, so that's a great question. First of all, whoever was in the audience, I didn't pay them unless it was Shivan. So actually, that's a great question. So as was alluded to, currently our benchmark suite includes BERT, which is a fairly small model, under 1 billion parameters. I think it's 300 million in BERT large. We actually are going to have a GPT-3 style model with hundreds of billions of parameters in the next round of MLPerf training in Q2 of this year. So stay tuned. It's under development. I'm super excited about it. And I did not pay whoever asked that question.
All right, thank you so much.
Yeah.
And David, by the way, I really like, every once in a while you will come up with a small joke. I think that's pretty good. Now,
humor makes life better.
Yep, yeah, definitely. Now let's get to this super long. I think it's also a challenging question. So I think the audience is asking, so network security is fundamental to any system, especially for the automotive system, right? So if security is so important, have you ever thought about put that into the performance measurement of your benchmark?
Yeah, that's a really great point. And I should probably update that slide, right? Security is super relevant to performance, right? Without security, performance is sort of useless and it gets turned against you. In a lot of cases, it's an afterthought. Actually, I'm not an automotive expert, but my understanding is actually security is, first of all, a very important thing for the automotive industry. And actually, there are very interesting applications of machine learning in security for things like intrusion detection and so forth. So it is not a component of our benchmarks. They are focused on performance only. I think we will probably see in the not distant future more collaboration between ourselves and folks in the security space, because it is absolutely so fascinating. And in particular, one of the things that is great about security for ML is there's such a high volume of network traffic, you can't ever hope to have a human look at it, right? There's just a lot of things where machines are producing the data, and the only way to get a handle on it is something like machine learning, right? And I think network security and security in general is a great example of that. I think machine learning will be a very powerful tool there, and we are working on some things. And if you're interested, shoot me an email.
Thank you very much, David.
Yeah.
I think all the audience are still digesting you. I think you present all things there. I'm pretty sure there'll be more questions.
I got a private question, actually. Do you mind if I read it out?
Go ahead, please.
Okay. So someone asked me, is it economical to use large models for automotive training? So, and that's a really good question. So first of all, there is a relationship between the size of the model when you're training and the performance for inference, right? Because fundamentally, inference is just the forward pass of the training loop. And so if you have a gigantic model, even the forward pass can be really challenging. And we see that today with models like ChatGPT, where actually or BARD, where even doing the inference might take multiple servers. So, the answer is really large models are not realistic to deploy in a car. And there's a second reason as well, which is automotive folks are very conservative. They don't want cutting edge models. They want models that are well understood and well characterized and don't have very weird bugs in them. And so that means you need to take some time to inspect them. And we're really just entering the era of really large models. But, one of the beautiful things about semiconductors and circuit design and the work that we all do in that area, and I do have a background in semiconductors, is that semiconductors and what Moore's law, may he rest in peace, and to great credit to this industry, Moore's law tells us transistors get cheaper over time, and we should be using those transistors to do more compute. And so the reality is, we cannot do gigantic multi-billion parameter models in a vehicle today, but my hope is that in the future we will be able to do that, right? And as we get more transistors and put them into the car, that will ultimately translate into more features, more capabilities, more intelligence. And, don't forget, right, what's the point of all of this? It's really saving lives on the road, more, better ecological impact, more power efficiency. So there's a lot where, this ML, particularly in automotive, can really impact society, right? Tens of thousands of people die on the road every year. If we can cut that by an order of magnitude, that would be amazing. So big models in cars today, probably not, but with our work together, maybe tomorrow.
Thank you so much, David. I think for the sake of time, we will have to move on to the next speaker. But again, thanks a lot for that
Perfect.
incredible talk.
Thank you very much.